Hey everyone, welcome. Today we're going to unpack a really beautiful and honestly super elegant concept from abstract algebra, the coset. So let's just jump right in with a big question. How in the world do we find simple repeating patterns inside these enormous, complicated systems? This is the kind of puzzle that gets mathematicians really excited, and as you'll see, cosets are one of their most powerful tools for cracking it. To get our heads around this, we're going to start somewhere familiar. We're going to build a world of structure using a simple analogy, a library, to build our understanding from the ground up. Okay, so I want you to picture a gigantic library. I mean, books everywhere. To make any sense of it, you wouldn't just stare at the whole chaotic mess, right? Of course not. You'd organize it. You'd put all the science fiction over here, all the history over there. You'd sort it by genre. This basic idea of breaking down a huge collection into smaller, more manageable pieces, that is exactly what we're aiming for here. Now, before we can actually build a coset, we need to get a handle on its essential building blocks. And in the world of algebra, these are called groups and subgroups. First up, the group. This is just the fancy word for the entire collection of stuff we're looking at. In our analogy, the group is the whole library, every single book on every single shelf. The whole shebang. And a subgroup? Well, that's just a smaller, self-contained collection that lives inside that bigger group. Think of it like the science fiction section. It's definitely part of the library, yeah, but it's also its own complete little world that follows all the same rules. All right, so we've got our group and we've got our subgroup. The foundation is set. Now for the main event. Let's actually build a coset. And for this, we're going straight to the source. This right here, this is the formal definition pulled from a classic algebra textbook. This is where the idea is officially born. Let's zoom in on the most important part. It says the set hat equals ha, where h is an h is called a right coset. Now, I know that looks pretty dense and full of symbols, but trust me, we're going to break it down into a super simple recipe. So how do we actually do it? It's basically a three-step process. First, you start with your subgroup H, our science fiction section. Second, you go out into the entire library, G, and you pick any one element A. Could be any book. And third, you take that element A and you combine it with every single element inside your subgroup H. And that new collection you just created, that is your coset, HA. You know, the source material also gives them another name, residue classes. It's a great way to think about it. It's like having a bunch of puzzle pieces. Each coset is a distinct piece, and when you put them all together, they perfectly form the bigger picture of the group, with no overlaps at all. And get this, here's a really cool little fact from the source. The original subgroup, H, is actually a coset itself. This happens when that element, A, you pick, is what's called the identity element. Just think of it as a do-nothing operation, like multiplying by 1. If you combine every book in the sci-fi section with the do-nothing element, you just get the sci-fi section right back. Pretty neat, huh? Okay, but wait, there's a little twist here we have to talk about. The recipe we just followed created what's called a right coset. Let's see what happens when we switch things up a bit and talk about right versus left. And this shows the difference perfectly. A right coset, Ha A, is what you get when you stick your element A on the right side of everything from the subgroup. A left coset, AH, is when you stick A on the left. Now, you might be thinking, come on, does that tiny change in position really matter? Well, like a lot of things in math, the answer is, it depends. Our source text spells it out for us. It says if the group G is abelian, then the right coset and the left coset are going to be exactly the same. An abelian group is just one where order doesn't matter. You know, like how 2 plus 3 is the same as 3 plus 2. But, and this is a huge but, in a non-abelian group, order is everything. Think about putting on your socks and then your shoes. You can't just reverse that order and expect it to work. In those kinds of groups, the left coset and the right coset can be two totally different collections of things. So, okay, we've defined them, we've built them, we know there's a left and a right version, but who cares? Why does any of this actually matter? Let's pull back and look at the bigger picture. Here is the real payoff. Our source material points out these key properties. Cosets are always part of the main group. They're never empty. And here's the most important part. They chop up the entire group into these separate non-overlapping chunks that are all the exact same size. It's like you're tiling a huge floor. Every tile is identical and they fit together perfectly with no gaps. That's what cosets do for a group.
So, if there's one thing you should take away from this, it's that cosets aren't just some random abstract idea. They're like a blueprint. They reveal the deep internal structure and the hidden symmetries of a group in this really beautiful, profound way. They let us see those repeating patterns we were looking for at the very beginning.
Ultimately, cosets are a tool that helps us map the hidden symmetries of these complex abstract structures. And it kind of makes you wonder, doesn't it? What other hidden patterns in math or physics or just in the universe are out there, just waiting for us to find the right tools to see them?